Welcome to the course on advanced power electronics. We'll cover today this single phase voltage source inverters. So coming to this detail of single phase voltage source inverter. The function of voltage source inverter is to convert constant DC voltage, which can be realized by an electrolyte capacitor or a battery, to AC voltage, which are segments of input DC voltage. An inverter is called voltage source inverter if the input voltage remains constant, and current source inverter if the input current is maintained constant. The output of the voltage waveform of ideal inverter should be sinusoidal. However, practical inverter waveforms are non-sinusoidal and contain certain harmonics. And for low and medium power applications, square wave and or quasi-square wave voltages are sometimes acceptable. The variable voltage can be obtained by varying the input DC voltage and maintaining the gain of inverter constant. On the other hand, if the DC voltage is fixed, then variable output voltage can be obtained by varying the gain of the inverter, and this can be accomplished by pulse width modulated control within the inverter, and the inverter gain may be defined as a ratio of the AC output voltage to the DC input voltage. Now coming to application of single phase voltage source inverters, the very interesting example is the single phase uninterruptible power supply. As you can see, in single phase domestic inverter, then single phase voltage source driving the single phase self-acting induction generator, then the single phase VSI for driving single phase self-acting induction generator in hydro, then electronic ballast, welding application, power supply for small fans, telecommunication power supply for instruments, power supply for medical equipment, switch mode power supply, printer power supplies and laptop power supply, desktop computer power supply, then power supply for single phase motors, then single phase 115 volt emergency power supply for aircraft cockpit, then photovoltaic array power generation, and then single phase shunt active filter, then single phase series active filter. Now coming to the performance parameters, the harmonic factor of nth harmonics, HNI. The harmonic factor, which is a measure of individual harmonic contribution, is defined as HFN equal to Vn upon V1, and where V1 is the RMS value of the fundamental component and Vn is the RMS value of nth harmonic component. And the total harmonic distortion is a measure of closeness in shape between the waveform and its fundamental component, is defined as TAD equal to 1 upon V1 and in bracket summation of all the harmonics up to 2 to n square, and distortion factor indicates that the amount of harmonic distortion that remains in particular waveform after the harmonics of that waveform had been subjected to second attenuation divided by n square. So distortion factor of an individual or nth harmonic component is DFN equal to Vn upon n square V1. And lower order harmonics, the lowest order harmonics is that harmonic component whose frequency closest to the fundamental one and its amplitude is greater than or equal to 3% of the fundamental component, and the TAD is under root summation of all harmonics other than fundamental is square divided by V1, and distortion factor V1 upon Vrms, and TAD is Vrms square minus V1 square under root divided by V1, or under root Vrms upon V1 square minus 1, or under root 1 upon DF square minus 1. Now coming to voltage source converters are classified like a single phase inverter. So single phase inverters are designed to supply AC power to single phase loads, and they are commonly used in residential applications such as powering household appliances and small scale renewable energy systems. These inverters typically consist of 2 or 4 switches, enabling them to generate an AC output with controlled frequency and amplitude. And now 3-phase inverter. 3-phase inverters are used to drive 3-phase loads such as industrial motors and grid connected power systems. They are essential in high power applications, delivering balanced 3-phase output with 4-order harmonic distortion, and their design typically includes 6 switches, enabling precise control over the voltage, frequency and phase angle. Now coming to classification of single phase inverters, these are classified like single phase half bridge inverter, single phase full bridge inverter and push pull inverter. Now these are typically the half bridge inverters with different kind of load, like half bridge for resistive load, half bridge for inductive load, half bridge for resisting load, and a half bridge for motor load. These are typical example of half bridge inverter. where the midpoint is used as a 1.4 AC and another midpoint between the two discharges is the another terminal of AC output. And this is the typical waveform of, you can say, a half bridge, that you have a voltage waveform and of course the fundamental current drawn by the load if it is a RL load, and then you have a typically the, you can call it a resistive load current, and then the load current with highly inductive load. Resistive load will follow the same waveform as the typically the voltage, but in case of inductive you will get a typically the waveform kind of triangular wave. Vs upon 4FL is the amplitude, and the output voltage VO equal to, in bracket, 2 upon T0, 0 to T by 2, Vs square by 4 dt to power half equal to Vs by 2, and the V1 equal to 2 Vs by root 2 pi, that is equal to 0.45 Vs. So coming to single phase full bridge inverter. So in single phase bridge inverter also we get the square wave, and then typically the current again can be a fundamental of this, and here if in case of resistive load it will be the same waveform, but RL load it will be lagging load, but inductive, pure inductive load you will get a triangular wave here also with the highly inductive. So the output voltage here also in RMS value 2 upon T0, 0 to T by 2, Vs square dt equal to Vs, and V1 equal to 4 Vs upon root 2 pi, that is equal to 0.9 Vs. And this is typically, you can call it the single phase full bridge inverter with different loads like R load, RL load, then inductive load, motor load. And if G1, G2 are the gating signal for switches Q1 and Q4 respectively, the switching function is S theta equal to G1 minus G4, and S theta is 1 for theta to pi, and S theta is minus 1 for pi to 2 pi, as you can see in the waveform. And if F0 is the fundamental frequency of the inverter, theta equal to omega t 2 pi F0 t, and S theta can be expressed in a Fourier series as S theta equal to A0 by 2 plus summation of n1 to infinity in bracket an cos n theta plus bn sin n theta, that is bn equal to 2 upon pi 0 to pi S theta sin n theta d theta, or equal to 4 upon n pi, or n equal to 1 to 1 3 or so. And due to half wave symmetry, A0 equal to an equal to 0, and substituting A0 an and bn in the, it develops equation S theta equal to 4 upon pi and 135 to infinity sin n theta upon n. And if the DC voltage is theta is Vs, then the output voltage can be obtained from the switching function as V theta equal to S theta into Vi theta, that is 4 Vs divided by pi, and summation of n equal to 1 all odd harmonic 135 pi to infinity sin n theta by n. So these type of inverter require a center tap push pull inverter. These type of inverter require a center tap primary, and push pull inverter can operate in pulse width modulator or square wave mode, and the waveform are identical to those of half bridge and full bridge inverter. The output voltage equal to V01, that is fundamental, MA Vd upon n for m less than 1, and Vd upon n, I mean V01 in between Vdn and less than V for y by Vd upon n for m greater than 1. This is the circuit of full push pull inverter, where the two switches, I mean with the anti-parallel diodes, are there, and have a midpoint in case of full pull, but the advantage is the only one device conduct at a time. The losses in the devices are less. Then advantage, the main advantage of push pull circuit is that no more than one switch is in series conduct at any instant of time, and efficiency is increased significantly, and gate drive circuit is simplified. And disadvantage, it is difficult to avoid DC saturation of the transformer, and the ripple in the inverter output voltage is square wave. I mean you can clearly see how it is the typically square wave and fundamental in that, and the ripple out of that fundamental is square wave minus fundamental, you can see clearly the ripple, and the corresponding there will be a ripple current also in the inductor. And if it is a pendulum inverter output voltage, pendulum bipolar voltage, then you can see the ripple are reduced, and you can see how the ripple voltage changes difference between the two, like a sine wave and the pendulum wave. And now what are the typically in case of voltage control for single phase inverter? Commonly used techniques are single phase pulse width modulation, multiple pulse width modulation, and sinusoidal pulse width modulation, and modified sinusoidal pulse width modulation, and transfer connections. So these are the techniques which are commonly used for control. This is the single pulse width modulation, and you can control the width of the first to control the output voltage or to eliminate one particular harmonic. How it is, you just compare typically the kind of sawtooth with your reference voltage, and then the pulse width is accordingly decided, as you can see here for devices. And output also you can see, which looks like a Cauchy square wave with the width of typically of the delta angle. So now in case of your waveform, here you see it is a plus minus delta by 2 on over the pi by 2. So you can say output RMS voltage is 2 upon 2 pi minus L delta by 2 to pi plus L delta by 2 Vs square d omega t to power half, and here V O equal to Vs under root delta upon pi, and where delta varies from 0 to 180 degree and VO varies from 0 to Vs. So coming to compare the for single pulse with modulation, compare the reference signal with carrier, and frequency of reference signal determine the frequency of output voltage, and the modulation index M equal to AR upon AC, and VO equal to N equal to 1, 2, 3, 5, 2, 4 S upon N pi sin N delta upon by 2 into sin N pi by 2 into sin N omega t, and where the typically T1 is here, if you look into the waveform, T1 is alpha upon omega is 1 minus M Ts by 2, and T2 equal to alpha 2 by omega 1 plus M into T by Ts by 2, and pulse width come D equal to delta by omega T2 minus T1 equal to MTS. And these are typically harmonic profile, different harmonic profile, like with the how with the modulation index the fundal varies, how distortion factor varies, and how the different harmonic like fifth, third, fifth, seventh varies. So now there is only one pulse per half cycle, and with the pulse is varied to control the inverter output voltage. So gating signals are generated by comparing the rectangular reference signal of amplitude AR with rectangular carrier wave of amplitude AC. The ratio of AR to AC is the control variable and defined as amplitude modulation index, and the dominant harmonics is the third, and the distortion factor increases significantly at lower output voltage. And these are multiple pulse width modulation, as you can see with the sawtooth, how is compared with the reference square wave, and the width of the pulse is, you can in this case almost it is symmetrical, I mean of the different pulses for positive and negative half cycle. And this is a typically per half cycle or the kind of on this gating pulses, how the output voltage is there at the width of delta angle, and then the function of carrier wave signal. To compare the reference with carrier, and frequency of reference signal determine the output voltage frequency, and frequency of the carrier determine the number of pulses per half cycle, and modulation index controls the output voltage. So the RMS value of the output voltage for multiple pulses per cycle can be calculated as VO equal to in bracket 2p upon 2 pi and integral from pi by p to minus delta by 2 to pi by p plus delta by 2, and Vs square d omega t square root of that, and VO equal to Vs under root p delta by pi. And then from this Fourier series of this output VO equal to and varying 1, 3, 5 all odd harmonics to infinity Bn sin n omega t, and Bn the Bn equal to your M equal to 1 to 2 pi for Vs upon n pi sin delta and delta by 4 in bracket sin n alpha m plus 3 delta upon 4 minus sin n in bracket pi plus alpha m plus delta by 4. So here the time instances of intersection points are Tm equal to alpha m upon omega, that is m small m minus capital M Ts by 2, and Tm equal to alpha m equal to omega m minus 1 plus M Ts by 2, and the pulse width d or pulse delta angle d equal to delta upon omega, that is Tm plus 1 minus Tm equal to MTS. And this is the typically the harmonic pattern, I mean for pulse, this identical pulse, and then how the distortion factor and fundamental and different harmonic varies with the modulation. The harmonic content can be reduced by using several pulses in each half cycle of the output voltage, and this type of modulation is also known as uniform pulse width modulation, and where the P equal to Fc upon 2F0, that is carrier frequency into 2 into frequency of reference signal, that is MF by 2, and where MF is defined as a frequency modulation index ratio. So larger the value of P, the lower the order of harmonics will be lower, but the amplitude of some higher order harmonics will increase. However, such harmonics produce negligible ripple or can be easily filtered out. So coming to sinusoidal pulse modulation, so instead of maintaining the width of all pulses the same in case of multiple pulses modulation. The width is varied in proportional to the amplitude of a sine wave evaluated at the center of same pulse. The distortion factor and lower harmonics are significantly reduced, and the number of pulses per half cycle depends on the frequency, and this type of modulation eliminate all the harmonics less than equal to 2p minus 1. For p equal to 5, the lowest harmonics will be 9, and these are typically single phase pulses modulated voltage source inverter of single phase bridge type, which are popularly used. And you can just have now pendulum control with the unipolar and bipolar switching. So you can say control voltage and triangular wave, and the output voltage typically the bipolar nature with the fundamentals shown dotted here VO1. So a small percentage of third harmonics can be added to the reference voltage in a voltage source converter to increase the amplitude of fundamental component without exceeding the DC link voltage limit. This technique improves the utilization of DC voltage and enhances the whole efficiency of the inverter. And this is typically kind of sampled with low frequency carrier wave, how clearly the computer output, how the getting signal, how the output voltage. And this is a sample pulse modulation with the high frequency carrier wave, and how the typically your output pendulum voltage and the load current typically vary for. And now coming to the pendulum with bipolar voltage, that you can see how it is the fundamental and plus minus voltage vary. So coming to pendulum with bipolar switching, so diagonally opposite switches TA plus and TB minus or TB and TB plus and TA minus form the two legs are switch and edge switch pairs 1 and 2 are respectively. The output voltage waveform inverter leg A is identical to the output voltage of a single leg inverter operating with the same switching scheme, and the output of inverter leg B is equal to the magnitude per opposite in sine 2 of leg A, and the output voltage V0 switches between minus PD to plus PD voltage level, and that's the reason this type of switching called the pendulum with bipolar switching. And this is typically the pendulum with the unipolar switching, where you can clearly see that the two carrier wave, with the carrier wave two control signal 1 plus and 1 minus are compared, and you get the getting signal G1 G4 and the output voltage that is unipolar. In the positive half cycle you get only the pulses of positive side, and for negative half cycle you get pulses of negative side. And you can clearly see the number of pulses in one half cycle is equal to the double the pulses of the getting signal, and that's really called also double pendulum also, this kind of switching. And certainly have advantage that the ripple here, because of increased ripple frequency, your filter requirement reduces. And these are typically how the pendulum with unipolar voltage switching. The one way that you can take two carrier, one plus modulating signal plus minus, or you can take a carrier with the plus minus and reference can be the same. So both the way you can generate the pendulum with the unipolar switching. And these are typically output waveform with the Fourier. If you look into of that, so you have a fundamental 0.8 here, and then you have a 2 MF sideband of 2 MF 1 and 2 MF plus the harmonics, and then you have a harmonics again order of the 2F 4F sideband typically. So in pendulum with the unipolar voltage switching, the switches in the two legs of the full bridge are not switched simultaneously, and here legs A and B of the full bridge inverter are controlled separately by combining V triangle with the V control and another with minus V control respectively, and output voltage changes 0 and V plus VD, or in between 0 and minus VD voltage level. Hence this type of pendulum scheme called a unipolar switching scheme, and this scheme has the advantage of effectively doubling the switching as far as the output harmonics are concerned as compared to the bipolar switching scheme. This coming to typically the voltage jumps in the output voltage at each switching are produced to VD as compared to 2 VD in the previous scheme. The advantage of effectively doubling the switching frequency appears in the harmonic spectrum of the voltage waveform, and here the lowest harmonics, that is idealized, appears as a sideband of the twice the switching frequency, and the RMS output voltage V equal to Vs M equal to 1 to 2 and delta M by pi to power half, and delta M is the width of the mth pulse, and the Fourier coefficient of the output voltage Bn equal to M equal to 1 to 2 by 4 Ps upon N pi sin N delta upon 4, and in bracket that is sin alpha M plus 3 delta by 4 minus sin N in bracket by plus alpha M plus delta by 4, where N equal to 135, and the time instances for intersection point can be found out. Tm equal to alpha m by omega, that is equal to tx plus m ts by 2, and the value of tx can be calculated as 1 minus 2 t upon t capital Ts equal to m sin in bracket omega in bracket tx plus m ts by 2, where the ts equal to t upon 2 in bracket p plus 1, and the mth pulse width dm or pulse angle delta m equal to tm equal to delta m by omega, that is tm plus 1 minus tm. And is the harmonic profile of typically a pulse width model inverter. You can see how it is the different harmonics. It depends on switching frequency. So what are the harmonic? Like starting typically like 11, 9, 11, 13, 15, and for P equal to 5, and how the distortion factor varies with the modulation index. Like, and this is the analysis of single pole bridge with sinusoidal pulse modulation. So you can see in the here also you have a, if carrier you really make a plus minus, but reference same, that this gives the similar effect as in case of previous one, and you can see the how you are getting bipolar, typically the voltage of unipolar nature in both positive half cycle. So we call it typically if G1, G2 are weighted signal for switching Q1 and Q4 respectively, the switching function S theta is G1 minus G4, and S theta can be expressed in terms of Fourier series. S theta equal to 0 by 2 plus function n 1 to infinity in bracket n cos n theta plus bn sin n theta, and where n theta 2 upon pi 0 to pi is S theta cos n theta d theta, that is 4 upon pi m equal to 1 to 3 to p, that becomes minus 1 to power m sin n alpha m, and due to symmetry a0 and bn equal to 0. So if the input voltage v I theta equal to vs, the output voltage becomes your theta equal to 4 vs upon n pi, and when n varies 1 3 5 to infinity, and that is, and plus in bracket the m varies from 1 to 3 to m, and that is minus 1 to power m sin n alpha m and cos n theta. So the carrier wave is applied during the first and last 60 degree interval per cycle, that is Eg 0 to 60 degree and 120 to 180 degree. This type modulation called modified sinusoidal pulse width modulation. The fundamental component is increased and its harmonic characteristics are improved, and it reduces the number of switching of power devices, which in turn reduces the switching loss. And this is typically the modified sinusoidal pulse modulation. How the typically, I mean, you have a different kind of symmetry of carrier wave, and you compare with the sinusoidal, and how the output voltage, I mean, getting signal are there, and you have get a typically the voltage waveform. So here again P equal to 5, you can see the harmonic variation, first fundamental, third 13, and with the DF distortion factor. So coming to advanced modulation techniques, I mean, sinusoidal pulse width modulation, while widely used, has a certain drawback, such as relative low fundamental output voltage. Alternative modulation techniques that provide enhanced performance include trapezoidal modulation, staircase modulation, step modulation, harmonic injection modulation, and delta modulation. And coming to trapezoidal modulation, the gating signals are generated by comparing a triangular carrier with the modulating trapezoidal wave, and the trapezoidal wave can be obtained from the triangular wave by limiting its magnitude to plus minus AR, which is related to the peak value AR max by AR equal to sigma AR max, where sigma is called the triangular factor because the waveform becomes a triangular wave where delta equal to 1, and the modulation intake M equal to AR upon AC, that is sigma AR max upon AC, or M varies 0 to 1. And these are typically how you modify the AR typically max for getting signal, and you get output voltage of bipolar nature. So now coming to staircase modulation, the modulating signal in this technique is a staircase waveform, and the step level of the staircase are designed to eliminate a specific harmonic, ensuring the improved output quality. And the modulation frequency ratio and the number of steps are carefully selected to achieve the desired output voltage characteristic, and this optimized pendulum method is generally not recommended for P rather than 15 pulses per cycle. So the optimum number of pulses per cycle is 15, and for 2-level inverter, and 21 for 3-level inverter, and 27 for 4-level inverter. This approach provides a high quality output voltage, achieving a fundamental component of up to 0.94 Vs, and the modulating signal is a step waveform but not a sampled approximation of a sine wave. So the waveform is divided into specify intervals such as 20 degree with each interval controlled independently to adjust the magnitude of the fundamental component and eliminate the specific harmonic. And this control method achieves lower distortion and a higher fundamental amplitude compared to the standard film technique. And this is typically how your reference signal is there, is staircase kind compared with the triangular where how the output voltage is there, and then further another kind of waveform and output voltage. So coming to selective harmonic injection modulation, the modulating signal is generated by injecting selected harmonics to sine wave, and this results in a flat top waveform and reduces the amount of overmodulation, and it improves the higher fundamental amplitude and lower distortion of output voltage. That is VR equal to 1.15 sine omega t plus 0.27 sine 3 omega t minus 0.029 sine 9 omega t. So the injection of third harmonic does not affect the quality of the output voltage because the output of three-phase inverter does not contain triple harmonics, and selective harmonic injection can improve the utilization of DC bus voltage, allowing for the increased fundamental output without entering overmodulation. And the method ensures that the injected harmonics are in phase aligned to cancel out the line-to-line voltage, thereby maintaining a high output quality and in three-phase system. And these are typically selective harmonic approach where we compare the reference signal with the modulating and how the output voltage is there. So another is the delta modulation. In delta modulation, rectangular wave is allowed to oscillate within a defined window delta V above and below the reference value. Here the inverter switching function, which is identical to output voltage VO, is generated from the vertices of the triangular wave VC, and it is also known as hysteresis modulation. So if the frequency of the modulating wave is changed, keeping the slope of the triangular wave constant, the number of pulses and the pulse width of the modulation wave would change, and the delta modulation can control the ratio of voltage to frequency, which is desirable feature, especially in case of AC motor control. And you can clearly see how the delta modulation with the hysteresis band upper and lower are there, and how the gating pulses are generated. So coming to inverter circuit design, the voltage and current rating of power devices in the inverter circuit depends on the type of inverter, load, and method of voltage and current control. And the design requires deriving the expression for the instantaneous load current, plotting the current waveform for each device and component. The voltage rating requires establishing the reverse voltages of each device. And to reduce the output filter are necessary, like C filter is very simple but draws the more reactive power, and LC filter can eliminate the only one harmonic. So a properly designed CLC filter is more effective in case of reducing harmonics of wide bandwidth and draws the less reactive power. And these are different filters like capacitor filter, LC filters, another kind of series LC filter, and then CLC filter. So now coming to harmonic reduction in single phase voltage source inverters. So there are classification of harmonic reduction like phase displacement, bipolar output voltage notches, unipolar output voltage, and 60-degree modulation and transformer connection. So now coming to harmonic reduction, the output voltage control of voltage source inverter require varying both the number of pulses per half cycle and the pulse width that are generally by modeling technique. The output voltage contains odd harmonics for the frequency spectrum, and some applications require either a fixed or variable output voltage, but contains certain harmonics are undesirable, reducing certain effects such as harmonic torque and heating in the motor interference and oscillation. And coming to phase displacement technique, the output voltage is VAB equal to N123 to infinity 4 Vs upon N pi sine N alpha by 2 cos N in bracket omega T minus alpha by 2. So nth harmonics can be eliminated by proper choice of the displacement angle alpha if cos N alpha equal to 0. So where alpha equal to pi by N, and the third harmonics is eliminated if alpha equal to your 90 by 3, that's a 30 degree. So coming to bipolar output voltage notches, a pair of the unwanted harmonics at the output of single phase inverters can be eliminated by introducing a pair of symmetrically placed bipolar voltage notches shown as in figure. And this harmonic elimination method also results in low losses. The pulse number varies from 5 to 19. So as you can see how really fundamental voltage and other angles are there. So now Fourier series of output voltage can be expressed as V equal to n equal to 1, 2, 3, 5 to infinity Bn sin omega t, and where Bn, for Vs upon pi in bracket 0 to alpha 1 sin n omega t d omega t. Similarly, at alpha 1 minus alpha 1 to alpha 2 sin n omega t d omega t, and plus alpha 2 to pi by 2 sin n omega t into d omega t, that is equal to 4 Vs by pi, and that is in bracket 1 minus cos and alpha 1 plus 2 cos alpha n 2 divided by n. And equation can be extended in 2m notches per cycle, so that can have a Bn equal to 4 Vs upon n pi in bracket 1 minus cos 2 cos n alpha 1 plus 2 cos n alpha 2 and minus 2 cos n alpha 3 plus 2 cos n alpha 4 or so on plus n, and Bn equal to finally the 4 Vs upon n pi in bracket 1 plus 2 k equal to 1 to m minus 1 की power k and n alpha k divided by n for n f or for n 2135, where your alpha 1 alpha 2 up to alpha k less than pi, and the third and fifth harmonics will be eliminated if b3 and b pi equal to 0. So this equation Bn equal to 4 Vs upon pi in bracket 1 minus 2 cos n alpha 1 plus cos 2 cos n alpha 2 divided by pi n. So given the necessary equations to be solved, 1 minus 2 cos alpha 3 1 plus 2 cos alpha 3 equal to 0, and similarly another equation 1 minus 2 cos 5 alpha 1 plus 2 cos 5 alpha equal to 0, or here alpha 2 is 1 by 3 cos inverse cos 3 alpha 1 minus 0.5, and alpha 1 comes 1 by cos inverse in bracket cos 5 alpha 2 plus 0.5. So these equations can be solved iteratively by assuming that minimum alpha is 0 and repeated the calculation for alpha 1 alpha 2. This result alpha 1 equal to 23.63 and alpha 2 equal to 33.3 degree. Now this is the unipolar output voltage notches, and coming to the coefficient of Bn, so Bn equal to 4 upon pi 4 Vs upon pi in bracket 0 to alpha 1 sin n omega t d omega t plus alpha 2 pi by 2 sin n omega t d omega t, and that is equal to 4 Vs upon pi in bracket 1 minus cos 2 alpha 1 plus cos n alpha 2 divided by n, and the equation can be extended for m notches per half cycle. So Bn equal to 4 upon Vs upon n pi, and that is 1 plus k equal to 1 to m to power minus 1 per k cos n alpha k, or n equal to 1 to 3 1 3 5, and where alpha 2 is between L1 and L3, similarly less than typically less than pi by 2. So the third and fifth harmonics will be eliminated if 1 minus cos 3 alpha 1 plus cos 3 alpha 3 equal to 0, and 1 minus 5 cos alpha 1 plus 5 alpha 2 equal to 0. So solving these equations by addition, we get alpha 1 equal to 17.83 degree and alpha 2 equal to 37.97 degree. So now coming to the 60 degree modulation. 60 degree modulation, this modified pendulum technique can be applied to generate notches that will eliminate certain harmonic effectively in the output voltage as shown in figure below with the different angle like alpha 2, alpha 3, alpha 2. So the coefficient Bn is given by Bn equal to 4 Bs upon n pi in bracket alpha 1 to alpha 2 sin n omega t into d omega t, and plus alpha 3 to alpha 4 sin omega t d omega t, and plus alpha 5 to alpha 6 sin n omega t d omega t plus pi by 3 to pi by 2 sin n omega t d omega t, and that gives the Bn equal to 4 Vs upon n pi in bracket half minus k equal to 1 to m to and minus 1 to power k cos n alpha k for n equal all odd harmonics. Now coming to transformer connection, the output voltage of 2 or more inverter may be connected in series through a transformer, or to reduce or eliminate certain unwanted harmonics. The output of first inverter can be expressed as V01 equal to E1 sin omega t plus A3 sin 3 omega t plus A5 5 sin 5 omega t, and so on. The output of second inverter VO2 is delayed by pi by 3. So VO2 equal to A1 sin omega t minus pi by 3 plus A3 sin 3 omega t minus pi by 3 plus A5 sin 5 omega t minus pi by 3 plus, and these are the typical transformer connection to transformer connection and connected in secondary in series, and how the output voltage is obtained. So now coming to resultant voltage output is obtained by vector sum. So V equal to VO1 plus V2, and that is equal to root 3 A1 in bracket A1 sin omega t minus pi by 6 plus A3 sin 3 omega t minus pi by 6 plus A5 5 omega t minus pi by 6 plus the effective output voltage have been achieved by 1 minus 0.866, that is 13.4, due to phase shift introduced by transformer connection. This third harmonic is eliminated by leveraging transformer winding configuration, ensuring improved output quality and reduced harmonic distortion. So the inverter 2 is so gated that its output voltage is VO2, which is having 3 levels of output, plus, minus and the 0, and the output voltage waveform is given the name 3-level modulation, and the output voltage forms a series combination of inverter 1 and inverter 2 is obtained by superimposing the waveform by proper choice of D1, D2, D3 and D4. The amplitude of VO, third harmonic, third, fifth and seventh harmonics are eliminated, and this is the addition of circuit of pulse with moderated, typically series connected for the load, which give the number of levels in output voltage. As you can see here, that okay, how the three connected together, and you get the wave shape of the very, you can call it the staircase kind of waveform. So coming to tap changing in the inverter, by using taps on the transformer, use the harmonic content in the output voltage, and the individual control rectifiers are tuned on and off in the sequence indicated in the waveform of the output voltage, and the tap changing arrangement is effective for resistive load, but with the inductive load the control becomes more complex to produce the output voltage. And these are typically how you can say tap changing in case. So you have a transformer and primary side you have voltage with the push-pull kind of arrangement with the multiple, where you can switch on in a manner that the output voltage becomes the stair kind waveform with the harmonic elimination because of this circuit. And these are the tap changing in the inverter output voltage waveform. So coming to the boost inverter, the boost inverter, typically the single phase VSI uses the buck topology, which has the characteristic that the average output voltage is always lower than the input DC voltage, and thus if an output voltage higher than the input one is needed, a boost DC-DC converter must be used between the DC source and the inverter depending on the power and voltage level. This can result in a high volume, weight, cost and reduced efficiency. So the full bridge topology can, however, be used as a boost inverter that can generate an output AC voltage higher than the input DC voltage, and these are typically how we can connecting the two converter in parallel, and how the output waveforms look like. So consider the two DC-DC converter feeding a resistive load as shown in the above figure, and the two converter produce the DC bias sine wave output such that each source only produces a unipolar voltage as shown in the figure B. So the modulation of each converter is 180 degree out of the phase with the other, so that the voltage range across the load is maximized. Thus the output voltage of converters are described by V equal to VDC plus Vm sin omega t, and Vb equal to VDC plus Vm sin omega t. Thus the output voltage is sinusoidal given as V equal to Va minus Vb, that is 2 Vm sin omega t, and thus a DC bias voltage appears at each end of the load with the respect to ground, but the differential DC voltage across the load is 0. Now this is a circuit of boost inverter, for typically a one bidirectional boost converter and two bidirectional boost converter, and each converter current bidirectional boost converter is shown of course in next figure, and you can clearly see boost and control two boost which are shown in the typically in the B waveform. And the output of inverter can be controlled by one of the two methods. Use a duty cycle K for converter A and duty cycle 1 minus K for converter B, or use a different duty cycle for each converter such that each converter produces a DC bias sine wave output. And the second method is preferred as it uses controller A and B to make the capacitor voltage VA and VB follow a sinusoidal reference voltage. And this is the boost inverter equivalent, and typically how it's really the work, and the simplified equivalent circuit for typical converter A. So when the mode 1, when the switch S1 is closed and S2 is open, the inductor IL1 rises quite linearly, and diode D2 is reverse bias, and capacitor C1 supply the energy to load, and the voltage VA decreases. And mode 2, when the switch S1 is open and S2 is closed, the inductor current IL1 flows the capacitor C1 and the load diode, and the current capacitor IL1 decreases while capacitor is discharged. So average output voltage of converter A, which is under the boost mode, can be VA equal to VS1 minus K, and equivalent circuit during the two modes of operation. And then the average output voltage for converter operates in both, that is VA equal to VS1 minus K. The average voltage of converter B, which is operates in under the buck mode, can be found out VB equal to VS upon K, and thus the average output voltage is VA equal to VA minus VB, that is VS upon 1 minus K minus VS upon K, and that becomes the DC gain of the boost inverter can be VDC equal to VO upon VS, that is 2K minus 1 divided by 1 minus K into K, and K is the duty cycle. And it should be noted that the VO becomes 0 at K equal to 0. If the duty cycle is varied around the quiescent point of 50% duty cycle, there is an AC voltage across the load, and the peak output voltage equal to VO, peak equal to VM into equal to 2 VA minus 2 VDC. And because a boost converter cannot produce an output voltage lower than the input voltage, the DC component must satisfy the condition that VDC is greater than 2 VM plus VS. Moreover, VOKP equal to VS divided by 1 minus K minus 2 bracket VOPK divided by 2 plus VS, and thus the AC gain is GS equal to VO upon P upon VS, and that is equal to K upon 1 minus K, and the VO output becomes VS at K equal to 0.5. And the inductor IL that depends on the load resistance R and the duty cycle K can be found out IL equal to K upon K 1 minus K into VS upon 1 minus K R, and the voltage stress of the boost converter depends on the AC gain GAC, the peak output voltage VM, and the load current IL. And this is the gain characteristic of boost converter with the voltage gain with the duty cycle, how it varies with the AC gain as well as DC gain. And now coming to buck boost inverter, so the full bridge topology can be applied to be operated in buck boost inverter as shown in the above figure, and it has almost the same characteristic as the boost inverter, and it can generate an output AC voltage lower or higher than the DC voltage. This analysis of inverter is in steady state has been the same condition as the boost converter. Now coming to numerical examples. So coming to first numerical example, a single phase half bridge inverter has the resistive load of R equal to 0.4 ohm, and the DC voltage is Vs equal to 48 volt. Determine the A RMS output voltage and the fundamental frequency VO1, and B the average output power P0, and the C average and peak current of the each transistor. The solution is given Vs equal to 48 and R equal to 2.4 ohm, and the RMS value of the output voltage fundamental component is given VO1 equal to Vs upon root 2 pi, that is equal to 0.45 into Vs, that is 21.6 volt. And the RMS value of the output voltage given by VO equal to in bracket 2 upon T0, 02 by 2 Vs square by 4 dt to power half, and that is Vs by 2 equal to 48 by 2, that is 24 volt, and hence the output power is VO square by R, that is 240 watt, and the peak current of each transistor is equal to d4 by divided 2.4 10 ampere, and each transistor conduct for 50% duty cycle. The average current is 0.5 into 10, that is 5 ampere. So example 2, a single phase full bridge square wave inverter is connected to resistive load, and the DC voltage is 24 volt. The average output power is 500 volt. Determine the average supply current, total harmonic resistance, distortion factor, and total overall harmonic. So average supply current VI is equal to P upon Vs, that is 500 by 24, 20.83, and now VO1 equal to Vs upon root 2 pi, that is 0.45 Vs, and the average output voltage VO equal to Vs by 2. So the RMS harmonic voltage Vn equal to in bracket VO square minus VO1 square on root, and that is equal to 0.2179 Vs, and the TAD can be equal to TAD equal to 0.2179 Vs divided by 0.5 Vs, that is 48.43%. And C coming to C, that your in bracket n 35 to infinity VO n upon n square is square to power half, and that becomes equal to VO3 divided by 3 square to square. Similarly for, so that becomes 0.024 Vs, and distortion factor DF is 0.0424 to 0.45, that is 5.382%, and the lower order harmonics is that the harmonic component whose frequency is close to fundamental one, and its amplitude is greater than or equal to 3% of fundamental component. So VO3 equal to V1 VO1 by 3 and the DF3 equal to VO3 by 3 square divided by VO1, that is 1 upon 27, that is 3.7, which is greater than 3%. Hence, the lower order harmonics is VO3. Now coming to example 3, a single phase full bridge IGBT based voltage source inverter is operated single pulse width modulated, and the inverter operates at a frequency of 50 Hz. The DC source potential is 400 volt, and the each pulse has a duration of 6 millisecond. Calculate the load RMS load voltage, RMS value of the fundamental component of output voltage, and TAD of the output voltage. The solution is F equal to 50, T equal to 20 millisecond, per switch D equal to 0.6 millisecond, Vs equal to 400, omega at 314 radian per second, and D equal to delta by omega, that is delta equal to 1.884. The RMS voltage V equal to Vs under root delta upon pi. To putting value, it comes 309.83 volt, and VO equal to N135 into infinity 4 upon 4 Vs upon n pi into sin n pi, and delta upon 2, that is sin omega t, and VO equal to 4 Vs upon root 2 pi sin delta by 2, that is 291 volt, and the TAD of the output voltage is VO square minus VO1 square divided by VO1 square and 200. Putting a value, it comes 35.71%. Coming to example 4, in a single phase full bridge based pendulum voltage source inverter, input DC voltage varies from 295 to 325. The output voltage is required to be constant 200 volt, and the maximum load current assumed to be generally is 10 ampere. Calculate the combined switch utilization ratio. So in this inverter, VT equal to VD max equal to 325, IT equal to root 2 is I0, that becomes 14.48, and number of switches 4. The maximum volt ampere is 2000. So switch utilization is VO1 IO max divided by QVT IT. Putting a value, it comes 0.11. Now coming to example 5, a single phase pendulum voltage source inverter feeds 5 kilowatt to 30 kilowatt volt RMS 50 Hz, and single phase AC mains from a constant voltage DC bus, and the switching frequency is 20 kHz, and the AC inductor is 5 millihenry, and the power factor is corrected to close to unity, and pendulum modulation index is 0.9. Determine the A and input DC voltage, B RMS AC current, and the phase shift in fundamental component of pendulum voltage and supply voltage. Given solution, given P equal to 5 kilowatt to 30 volt 50 Hz, F equal to 20 kilowatt, LS equal to 5 millihenry, M equal to 0.9. So since the power factor unity, so IS1 equal to 5000 by 230, 21.74, and XL is 314 into 5 into N1 is 3, 1.57 ohm, and VO1 equal to Vs square plus ISXL square, that 232.5, and VD is equal to root 2 VO1 divided by M. So this becomes root 2 232.5 divided by 0.9, 365 volt, and IS equal to 21.74, and delta equal to sin inverse PXL upon Vs into V0. So putting value, it comes 8.44 degree. Now coming to example 6, a single phase voltage source inverter feeds the RL load of 5 ohm with a 0.8 lagging power. Calculate the current TAD. As you can, so V equal to 20 and J equal to 4 plus 3J, 5 ohm impedance at 0.45 lagging. Now the fundamental component will be given as I1 equal to V1 upon Z1, and putting a value 220 by 5, that's for 40 ampere, 44 ampere, and the harmonic current is given as IN equal to Vn upon Zn equal to V1 upon N 1 upon R plus Jxn, that is equal to V1 upon N under root R square plus Xn square. And from this equation, the third harmonic is calculated I3 V3 upon Z3, that is V3 by 3 1 upon R plus Jx3, and that is 220 upon 3 under root 4 square plus 3 into 3 square, and that is equal to 7.44 ampere. And now similarly, fifth and another dominant harmonics are calculated. I5 equal to V5 upon 5, and putting a value, it comes like a V5 1 upon R plus Jx5, that is 225 under root 4 square plus 5 into 3 square equal to 2.83, and I7 is V7 by 7, that comes equal to 1.47. I11 comes similarly 0.6016, and I13 becomes typically your 0.4 ampere. And now the harmonic content is IH equal to I3 I5 square I7 square up I13 square, that becomes 8.1 ampere, and TAD now IH upon I1, that is becomes 18.47%. Now coming to example 7, a single phase full bridge inverter have a RLC load with R equal to 10, L equal to 31.5 millihenry, and C equal to 112 microfarad. The inverter frequency is 60 Hz, and the DC input voltage is PS equal to 20 volt. So derive the expression for instance load current in the Fourier series and calculate the RMS load current at the fundamental frequency f0. Also the calculate the TAT of load current. The solution is Vs equal to 220, f0 equal to 60, R equal to 10 ohm, L equal to 31.5 millihenry, C equal to 112 microwatt, omega equal to 2 pi C into 60, 377 hertz, and the inductive reactance for the nth harmonic is XL equal to Jn omega L, and putting a value it comes J 11.87 and ohm, and the capacitive reactance for nth harmonic is X equal to 1 upon N J omega C, that becomes minus J 23.68 upon N, and the impedance for the nth harmonic is Zn value absolute I under root I square N omega L minus 1 upon omega, N omega C square, and that becomes in bracket 10 square plus 11.87 N minus 23.68 upon N square, and under root 2 1 by 2, and load impedance angle for the nth harmonic theta n equal to n inverse 11.87 N minus 23.68 N divided by 100 10, that becomes 10 inverse 1.187 N minus 2.368 upon N, and the VO equal to N equal to 1352 infinity for Vs and pi into sin n omega t, and VO equal to that 280.1 sin 377 t plus 93.4 sin 3 omega 3 into 370 t plus 56.02 sin 5 into 377 t plus 4 t plus sin 7 into 3 omega and plus 31.19 into sin 9 into 377 t plus further harmonic. So dividing the output voltage by load impedance and considering the appropriate delay due to load impedance angles, we can obtain the instantaneous load current. So that becomes I equal to 18.1 sin 377 plus 49.72 plus 3.17 3 sin 3 into 377 minus 70.17 degree plus sin 5 into 377 minus 70.5 degree and 0.5 into sin 7 into 337.82.85 degree 1.3 sin 9 in bracket 9 377 t minus 84.52 degree and plus 1. So the peak fundamental IM1 equal to 18.1 ampere, the RMS load current at fundamental you can say IO1 equal to 10.1 by divided through 12.8. Considering the up to 9th harmonic, the peak load current is IM equal to under root 18.1 square 3.1 square 1 square plus 0.5 square plus 0.3 square under root of that 18.41 is, and the nth harmonic current IH equal to IM square minus IM1 divided by root 2 to half, that becomes 2.3789 ampere. The TAD of load current is IM square minus IM1 to power half divided by M1. So putting value it comes 18.59%. Now coming to example 8, a single phase full bridge inverter connected to an industrial load having a instantaneous load current equal to 21.5 sin 314 t plus 35.8 degree plus 6.8 sin 942 t minus 69.15, and the load has a resistive component of 8 ohm. The higher order harmonics are neglected. The DC voltage is Vs equal to 20 volt. Calculate the load power and the fundamental output are also the find the average and average supply current and what will be the peak current through the industrial switches. The peak load current can be IM equal to under root 21.5 square plus 6.8 square, that is 22.55 ampere, and the RMS load current is I equal to IM of I root 2, that is 15.95, and load power is P equal to I square into R, that is 2.035 kilowatt, and fundamental power load power P equal to 21.5 divided by root 2 square into 8, that comes 1.848 kilowatt, and the average supply current I is equal to PO upon Vs, that becomes 9.25 ampere, and the peak switch current IP equal to I max equal to 22.55 ampere. Coming to example 9, a single phase full bridge inverter controls the power in a resistive load. The nominal value of input DC voltage Vs equal to 220, and the uniform pulse width modulation with 5 pulses per half cycle is used. Find the required control width of the pulse of 30 degrees. Determine the RMS voltage of load. If the DC supply increases by 10%, determine the pulse width to maintain the same load power. If the maximum possible width is 35 degrees, determine the minimum allowable limit of the DC source. So Vs equal to 20, P equal to 5, delta equal to 30. The RMS output voltage V equal to in bracket 2 P upon 2 pi, and pi P minus delta by 2 to P pi P plus delta by 2 Vs square d omega t under root 1 power 1 by 2, and that becomes Vs under root P delta upon pi. So putting the value, so VO becomes like a 200 volt and supply increases by 10, so that is 1.8 into 200 1.1 root 5 into delta by 80, so delta comes 24.75 degree. and if the maximum width is limited 35 degree, so that is 200.8 Vs into 5 into 35 divided by 180, so Vs comes 203.65 volt, and hence the minimum allowable DC supply voltage to maintain the same load voltage is the 203.65 volt. Coming to example 10, a single phase boost inverter consisting of two half bridge converters has a supply voltage of 220 volt. The converter rate duty cycle is 0.55. Calculate the average output of both the converters and the average output voltage of inverter, also the DC gain of the boost converter. The converter output is with the under boost mode, and hence its average output V equal to Vs upon 1 minus K, so it comes 489 volt, and the average output voltage converter B is V equal to Vs upon K, that comes 440 volt, and the average output is V equal to Va minus B, that comes 89 volt, and the DC gain of the boost converter GDC upon V upon Vs, that comes 0.4045, and these are the books which form is materially prepared, and thank you.